Welcome to this coding solution walkthrough. Today, we'll be exploring LeetCode problem number 1967, titled Number of Strings that Appear as Substrings in Word. This is a great problem to practice string manipulation techniques and improve your problem-solving skills. Let's dive in. In this problem, we're tasked with determining how many strings from an array called patterns appear as substrings within another string called word. A substring is simply a contiguous sequence of characters within a string. For example, if the string is ABC, its substrings include a, B, C, UB, BC, and ABC. The goal is to count how many of the strings in patterns can be found as substrings inside word. The input consists of the array patterns and the string word. The size of patterns can range from 1 to 100, and each individual string in the array can also range from 1 to 100 characters in length. The string word itself can be as long as 10,000 characters. The output will be a single integer that represents the count of matching strings from patterns that are substrings of word. To better understand the problem, let's look at some examples. In the first example, we are given patterns as ABC, BC, D, and word is ABC. The output here is 3. This is because ABC and BC are all substrings of ABC, but D is not. In the second example, patterns is B, C, and word is AAB. The output in this case is 2. This is because A and B both appear as substrings in AAB, but C does not appear. So, the result is 2. Now, let's explore a third example. Here, patterns is XYZ, XY, Z, and word is XYZZXY. The output for this case is 3 because all the strings in patterns are substrings of word. Specifically, XYZ appears as part of the sequence XYZZXY, XY appears at the start and again later, and Z appears multiple times. Thus, all 3 strings match, giving a result of 3. The constraints for the problem ensure that the size of the input is manageable. For instance, patterns will always have at least one string, and both patterns, I, and word will contain only lowercase English letters. We also need to consider special edge cases. For example, an empty patterns array is invalid since the constraints guarantee that patterns will always have at least one string. If word has only one character, only patterns with a single character can match. There are cases where no strings in patterns are substrings of word, resulting in an output of 0. Conversely, if all the strings in patterns match, the output will equal the length of patterns. Additionally, when the strings in patterns are very long, their ability to match depends on the content of word. Finally, with word being as long as 10,000 characters, the solution must efficiently check for substring matches to avoid performance issues. These considerations help ensure the problem is solved robustly for all valid inputs. To solve the problem of counting how many strings from the patterns array appear as substrings in the given word, we first consider the simplest approach, brute force. The intuition here is straightforward. For each string in patterns, we check if it exists as a substring in word using Python's an operator or an equivalent substring search function. Implementing this is very simple. We loop through each string in patterns, check if it is a substring of word, and increment a counter whenever we find a match. This method ensures we systematically check every string in patterns against word, making it easy to understand and implement. When analyzing the brute force method, we see that its time complexity is O, n asterisk m, where n is the number of strings in patterns and m is the average length of strings in patterns. The n operator itself operates in O, word, plus p, which is efficient when the strings in patterns are relatively short. Space complexity, on the other hand, is O, 1, because we do not use any additional data structures. While this approach is simple and easy to implement, it can become inefficient for very large inputs, particularly when patterns or word are lengthy. For cases where word is exceptionally long or substrings in patterns overlap significantly, we might explore alternatives like a sliding window approach. This method involves pre-computing substrings of word and storing them in a set for faster lookups, but as we'll see, its advantages are limited in Python due to the internal optimizations of the n operator. The sliding window approach has its own complexity considerations. The time complexity of pre-computing all substrings of word is O, word, 2, and checking each pattern string adds O, n, making it less efficient overall. Additionally, the space complexity is O, word, 2, because we store all substrings in a set for constant time lookups. While this method can be faster for repetitive or overlapping substrings, its high memory usage and computational overhead make it less practical for shorter pattern strings or smaller problem constraints. Alternatively, a more advanced technique like hashing can be considered. By using a rolling hash algorithm, such as Rabencarp, we can pre-compute hash values for substrings of word and compare them against hashed values of patterns. This reduces the complexity of the substring search but introduces additional challenges in terms of implementation and collision handling. Using a hashing approach, we achieve a more favorable time complexity of O word plus n, as pre-computing hash values for substrings of word takes linear time, and comparing hashes is constant. The space complexity is O word, since we only store hash values instead of all substrings. This method is particularly beneficial for very large inputs where the brute force approach could become inefficient. However, it comes with trade-offs. Hashing introduces implementation complexity, requires careful handling of hash collisions, and may not provide significant performance improvements given the constraints of this problem. For these reasons, we select the brute force approach as our strategy. It leverages Python's optimized substring search, making it simple and effective within the given problem constraints. The brute force approach provides the best balance between simplicity, efficiency, and readability for solving this problem. Its time complexity remains O, n asterisk m, where n is the number of strings in patterns and m is the average length of these strings. The space complexity is O, 1, as no additional memory is required beyond a counter. Given the problem constraints, which typically involve a maximum of 100 strings in patterns and a maximum word length of 10,000, this approach is both practical and efficient. While advanced techniques like hashing or sliding windows may offer theoretical benefits, their added complexity is unnecessary for this problem. The brute force method, with its simplicity and reliance on Python's optimized string operations, is the most appropriate choice. To solve this problem, we aim to determine how many strings from the patterns array appear as substrings within the given string word. Remember, a substring is any contiguous sequence of characters in a string. For instance, if the patterns array contains the strings at, ABC, and D, and the word is ABCD, both at and ABC are substrings of word, while D is not. The algorithm starts by parsing the input data, taking in the patterns array and the word string. The goal is to check each string in patterns to see if it exists as a substring in word. To achieve this, we first initialize a variable, count, to 0, which will keep track of how many matches are found. This sets up the foundation for the steps that follow. The next step is to iterate over the patterns array and check each string to see if it appears as a substring within word. For each string p in patterns, we use Python's in operator to check if p exists in word. If the condition evaluates to true, meaning the substring is found, we increment the count variable by 1. Once all strings in patterns have been processed, the algorithm concludes by returning the value of count, which represents the total number of matches found. This simple and direct approach ensures that we efficiently determine the result without unnecessary complexity. Let's walk through an example to see the algorithm in action. Suppose the input consists of patterns equals A, ABC, D, and word equals ABCD. We start by initializing the count variable to 0. Then, we iterate through the patterns array. First, we check if the string is a substring of ABCD. This is true, so we increment count to 1. Next, we check if ABC is a substring of ABCD. Again, this is true, so we increment count to 2. Finally, we check if D is a substring of ABCD. This is also true, so we increment count to 3. After processing all the strings in patterns, we return the final value of count, which is 3. This demonstrates how the algorithm systematically checks each pattern and tallies the matches. There are a few key insights that highlight the efficiency and robustness of this approach. First, Python's an operator is specifically optimized for substring searches, making it a concise and efficient tool for this task. The time complexity of checking if a string p is in word is O, n, where n is the length of word. Additionally, the algorithm only requires a single pass through the patterns array, which ensures that it remains efficient for smaller input sizes. It's also important to consider edge cases. If patterns is empty, the output is 0 because there are no strings to check. Similarly, if word is empty, the output is also 0 because no substrings can exist in an empty string. If there are duplicate strings in patterns, each duplicate is counted individually if it matches, which aligns with the problem requirements. The algorithm relies on minimal data structures, which keeps it both simple and memory efficient. The inputs consist of the patterns array and the word string. To track the number of matches, we use a single integer variable, count. Beyond this, no additional data structures are required, as the AND operator handles substring matching efficiently. When analyzing complexity, the time complexity is determined by the number of patterns and the length of the word. Let M represent the number of strings in patterns and N represent the length of word. For each string in patterns, the substring check P in word takes O, N, in the worst case. Therefore, the total time complexity is O, M asterisk N. The space complexity is O, 1, as no extra memory is allocated beyond the counter variable. While the current algorithm performs well for smaller input sizes, there are optimizations to consider for handling larger datasets. One such optimization is the Aho-Korosik algorithm, which uses a tree-based approach to pre-process the patterns array. This allows simultaneous substring searches, significantly reducing the overall time complexity for larger inputs. For the given problem constraints, the current solution is efficient and straightforward. However, understanding these advanced techniques prepares us for scenarios where scalability is critical. This Python implementation solves LeetCode problem 1967, number of strings that appear as substrings in Word, in an efficient and straightforward manner. Here's a line-by-line breakdown of the code. 1. Defining the class and function. The solution class encapsulates the method number of strings. This is a common structure for LeetCode problems, ensuring the solution aligns with the platform's expected input and output format. 2. Function input parameters. The method takes two parameters. Patterns, a list of strings to check. Word, the target string in which substrings are checked. 3. Initializing the count variable. A variable count is initialized to 0. This will keep track of how many patterns from the list are found as substrings in Word. For iterating through patterns, the for loop iterates over each string in the patterns list. This ensures that we systematically check every pattern against the target string. 5. Checking substrings. The if pattern in Word condition determines whether the current pattern exists as a substring within Word. The in keyword is a Pythonic and efficient way to perform this check. 6. Updating the count. If the condition is true, the count variable is incremented by 1. This step ensures that each matching pattern contributes to the final tally. 7. Returning the result. After all patterns have been checked, the method returns the value of count, which represents the total number of patterns found as substrings in Word. ### complexity analysis. Time complexity. The solution has a time complexity of O, N asterisk M, where N is the number of patterns and M is the average length of the patterns. The substring check pattern in Word is typically O, M, for each pattern. Space complexity. The space complexity is O, 1, as no additional data structures are used. ### edge cases. The code handles edge cases such as an empty patterns list, the loop is skipped, and the function returns 0. Patterns that are longer than Word, these will not match, as the substring check will return false. Duplicate patterns in the list, each occurrence is counted independently if it matches. This implementation is concise, efficient, and adheres to the problem requirements, making it a robust solution for the task. This is the Java implementation of LeetCode problem number 1967, number of strings that appear as substrings in Word. It mirrors the Python solution, using Java's string.contains method to check if each pattern is a substring of the given word. The logic is straightforward: iterate through the patterns array, increment a counter if a pattern is found in the word, and return the count. The main differences are Java-specific syntax like type declarations and the use of Java's string methods. To understand the solution, let's look at a basic example. Here, we have the patterns array containing a, ABC, and BC, and the word is ABC. We start by initializing a variable count to 0, which will track how many patterns appear as substrings of the word. The first pattern is a. We check if a is a substring of ABC using the in operator. Since it is the first character of ABC, this check returns true. We increment count by 1, so now count is 1. Next, we check the pattern ABC. Using the same approach, we see that ABC matches the entire word, so the check is true again. We increment count to 2. Finally, we check the pattern BC. Since BC starts at the second character of ABC, the check returns true, and we increment count to 3. At this point, we've processed all patterns, and the final value of count is 3. The output for the first example is 3, as all 3 patterns appear as substrings of the word. Now, let's consider a case where none of the patterns match. In this example, the patterns array contains D, EF, and GHI, and the word remains ABC. Again, we initialize count to 0. The first pattern, D, is checked to see if it is a substring of ABC. Since D does not appear in ABC, the check returns false, and count stays at 0. The next pattern is EF. Similarly, EF does not appear in ABC, so the check is false, and count remains 0. Finally, we check GHI. This pattern also does not appear in ABC, so the check is false again, and count remains 0. After processing all patterns, the final value of count is 0. The output for the second example is 0, as none of the patterns appear in the word. Now, let's explore a more mixed example where some patterns match and others do not. Here, the patterns array contains a, Z, EB, and X, and the word is still ABC. We start by initializing count to 0. The first pattern, is checked to see if it is a substring of ABC. Since it is the first character of ABC, the check returns true, and we increment count to 1. Next, we check the pattern Z. Since Z does not appear in ABC, the check returns false, and count remains 1. The next pattern is UB. We check if UB is a substring of ABC, and the check returns true because UB is the first 2 characters of ABC. We now increment count by 1, bringing the value of count to 2. The final pattern to check is X. Since X does not appear in ABC, the check returns false, and count remains 2. After processing all patterns, the final value of count is 2. The output for this example is 2, as 2 of the patterns, A and UB, appear as substrings of the word, while the other 2 patterns, Z and X, do not. When analyzing the time complexity of this solution, we begin by evaluating the operations involved. The solution processes each pattern in the patterns list, and for each pattern, it checks if it exists as a substring within the string word using the in operator. The first component of the complexity comes from the outer loop, which iterates over all k patterns. This contributes O, k, to the total complexity. Next, we consider the substring check itself, which is where the in operator comes into play. The worst-case complexity of this operation is O, m*n, where m represents the length of the current pattern and n represents the length of the word. This happens because, in the worst case, the in operator compares the pattern against every possible substring of word of length m. Since there are up to m plus 1 such substrings, and each comparison takes O, m, time, the total cost of this operation simplifies to O, n*m in the worst case. Now, considering the total time complexity, if we perform the substring check for all k patterns, the overall worst-case complexity becomes O, k*n*m, where m is the average length of the patterns and n is the length of word. On the other hand, in the best-case scenario, if a pattern is either empty or found immediately at the start of word, the substring check can be completed in O(1). Performing this for all k patterns would result in a total time complexity of O, k. Shifting focus to space complexity, the memory usage is determined primarily by the storage of the input, which includes the patterns list and the string word. These require O, k*m plus n, space, where k is the number of patterns, m is their average length, and n is the length of word. Beyond input storage, the solution uses no additional data structures. Scalar variables such as count and loop variables contribute only O(1) space. Therefore, the overall space complexity is dominated by input storage, resulting in O, k*m plus n. To better understand the efficiency of the provided solution, let's compare it with a brute force approach. A naive method would involve generating all possible substrings of word and then checking each pattern against these substrings. This approach has a significant drawback. Generating all substrings of word alone requires O, n squared, time. Then, for each of the K patterns, we would have to compare it against all these substrings, resulting in a total time complexity of O, K *n squared. The provided solution avoids this inefficiency by leveraging the in operator, which eliminates the need to explicitly generate substrings. When analyzing the best, average, and worst cases, we see that in the best case, if patterns are very short and found early in Word, the substring check takes constant time, resulting in a total complexity of O, K. On average, the substring check has a time complexity of O, n *m per pattern, leading to a total of O, K *n *m. In the worst case, when patterns are long and Word is large, each pattern requires a full substring search, which again results in O, K *n *m time. To solidify our understanding, we can mathematically prove the big O complexity of the solution. The in operator performs a substring search within Word of length n. For a pattern of length m, this involves comparing the pattern against up to n m plus 1 substrings, each taking O, m time. This yields a complexity of O, n *m, for a single pattern. When repeated for all K patterns, the total complexity becomes O, K *n *m. Regarding space complexity, the solution uses constant additional space beyond the input, which consists of the patterns list and the string word. This storage is proportional to the size of the input, i.e., O, K *m plus n. In conclusion, the solution optimally balances time and space efficiency, avoiding the significant overhead of naive approaches and performing well even in worst-case scenarios. When solving this problem, there are several common mistakes to watch out for. One big issue is not accounting for edge cases. For example, if the patterns list contains an empty string, it should always match any part of the word, but this is often overlooked. Another common oversight is ignoring case sensitivity. Remember that ABC and ABC are treated as different strings unless explicitly handled. Duplicate patterns can also cause problems, as they might lead to incorrect counts if not properly addressed. Efficiency is another area where mistakes happen. Using nested loops to manually check substrings can lead to a time complexity of O, n squared *k, which is far from ideal, especially when simpler methods exist. Finally, be cautious with how you use string methods. For instance, relying on == to check for substring matches instead of using methods like .find, or the in keyword can result in errors. Similarly, hardcoding assumptions about pattern lengths can cause your solution to fail when patterns vary in size. Avoiding these pitfalls will make your implementation both correct and efficient. Now, some variations of the problem require careful attention to overlapping matches, but this particular problem does not. Misunderstanding this can lead to unnecessary complexity or incorrect results. Shifting to interview-specific insights, there are key areas you'll want to focus on. First, you should be comfortable with basic string operations like .find, in, and slicing because these are foundational to solving string processing problems. Scalability is another important topic. While a straightforward approach like pattern in Word works well here, you should be able to discuss more advanced techniques, such as hashing or the Knuth-Morris-Pratt algorithm, especially in scenarios with stricter performance constraints. Clear communication is critical. Make sure to clarify edge cases, such as empty strings or unusual characters, early in your explanation. Additionally, explicitly discussing time complexity is always a good practice, even if you're using a simple solution. These skills will help you stand out in an interview. There are also several related problems on LeetCode that build on similar concepts. For example, problem 28, find the index of the first occurrence in a string, also focuses on substring searches, making it a great practice problem. Another is problem 139, word break, which involves checking if a string can be split into valid words from a dictionary. This problem takes substring checks to the next level by requiring additional logic for segmentation. Problem 392, is subsequence, is another related challenge, where you determine if one string can be derived as a subsequence of another. Finally, there's problem 520, detect capital, which tests your familiarity with string operations like handling case sensitivity. Exploring these problems can help you develop a deeper understanding of string manipulation and common patterns in competitive programming. To solve this problem, there are multiple approaches you can consider, each with its own trade-offs. The brute force method is the simplest. It involves iterating through each pattern and manually checking if it exists in the word. However, this approach has a time complexity of n squared asterisk k, which makes it inefficient for larger inputs. A better alternative is a set-based optimization, where you store all patterns in a set and iterate through the word, checking substrings of relevant lengths. This reduces redundant checks and improves efficiency to n asterisk k. For problems with overlapping matches or longer patterns, a sliding window technique can be used, which pre-processes the word string for substring matches and achieves a time complexity of n. If you're working with large datasets, a tree-based solution might be the best choice. By building a tree from the patterns and searching for matches in the word, you can achieve highly efficient lookups, though it does require additional memory. Choosing the right approach depends on the constraints and scale of the problem you're solving. Great job! We've successfully tackled LeetCode problem number 1967. In this session, you learned how to count substrings efficiently, reinforced string manipulation concepts, and practiced problem-solving strategies. If you enjoyed this walkthrough, be sure to like and subscribe for more coding content. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!